For our second example regarding the conservation of energy with the inclusion of work, we have the following situation. We have a spring that has a spring constant of 900 newtons per meter, and we're told that it has been compressed by 70 centimeters from its resting length. We've placed a 10 kilogram ball in front of that, and we are about to fire that ball forward. And all of this is taking place on top of an, let's say, 8-meter high hill. That ball is going to fly forward, it's going to move down that hill, and then it's going to roll onto a frictional section. And we're told that the frictional force that will act on that object is 40 newtons. And the question we're looking for is, once it's fired and it rolls all the way down that hill, and it's then on the frictional section, how far onto that frictional section will it roll before friction takes all of that energy away? As it starts to slide across that frictional section, it will slow the object down, convert that energy into things like heat and sound, which are non-mechanical forms, and that ball will eventually deplete all of its mechanical energy and come to rest. We want to know exactly how far from the front of that frictional section that ball is going to slide. So much like we did previously, we're going to start by defining our points and listing out our energies. So I'm going to define point 1 as prior to being fired, and point 2 will be at the end when the ball has literally come to rest and has no forms of energy anymore. So at the very beginning, point 1, we do have gravitational potential because we're 8 meters above our lowest point. Generally, we will assume the lowest point in any scenario, any diagram, that will be our 0 potential energy point. So we'll assume that this has gravitational potential due to that height. Hasn't been fired yet, so it has no kinetic energy. There is a spring. It's been compressed. There's therefore stored elastic potential energy. And if I look between point 1 and point 2, in order to go from 1 to 2, I do have to cross over some friction, which means work is present. It's going to act on the ball and change its energy, so I have to include work. At the end, there's nothing. It's on the lowest possible elevation, so no gravitational potential. It's not moving anymore because we want to find the point at which its final velocity is 0, so no kinetic. And the elastic potential energy no longer exists because it was in the spring at the beginning, but then the spring transferred all of that to the ball. So we have nothing left over at the end, and our simplified expression is the gravitational potential due to the height and the elastic potential due to the compressed spring at the very beginning, plus whatever work is performed by the friction must equal 0 mechanical energy at the end because the ball doesn't have anything. Now we can go ahead and we can substitute in our actual equations. So mgh plus 1/2 k delta x squared plus fd cosine theta must equal 0. All I've done is substitute in the actual equations for gravitational potential, elastic potential, and the work formula. I can then go ahead and I can plug in all my known values. So the mass is 10. Again, assuming this is Earth, the acceleration is 9.81. And the height was 8 meters. The K value is 900. I do have to convert 70 centimeters into 0.70 meters. If you don't do that, you'll get quite an interesting answer. The force of friction in this case, the force that's performing the work is 40. Friction is going to act 180 degrees against the distance that that object is covering, so the angle will be 180. And if you take a look at that entire equation, we have one unknown. So one equation, one unknown, we can solve for it. If we do our algebra correctly, we should find that it will slide exactly 25.13 meters before its kinetic energy is depleted. And again, that energy is not gone. It's just no longer in a mechanical form, a potential or a kinetic. It's now likely in heat or sound or something along those lines. So while it is still energy, it's no longer mechanical energy. It's not useful to moving this object. So we say that at this point, the mechanical energy will be depleted.